Welcome back to ECE 501B. As way of announcements, our first exam is in 2 weeks on the 28th of September, and homework number 3 is due the Monday preceding that. And that will be then the material that you will be held responsible for on exam number 1 is that material on homeworks 1, 2, and 3, and you can see what some previous exam number 1s have looked like in a review section or in the exam number 1 module on the website D2L. What I want to do today is continue with chapter 3, and there we were talking about surjective maps, which there's an R that's related to range spaces. And a surjective map is one that fully fills up or covers the entire output vector space. Then we will go through a fairly extensive example illustrating the null space and the range space, those concepts, and these will be non-trivial null spaces and range spaces. That leads us into the fundamental theorem of linear maps, which is a relationship between dimensions of these different subspaces, where the dimension of your input vector space, capital V, is actually equal to the dimension of the null space, which is a subspace within the input vector space, plus the dimension of the range space, which is actually a subspace of the output vector space. So we have this relationship that's crossing between the input and output spaces, but it relates to the dimension of your input vector space V. And it's a combination of the size or dimension of your null space and the size or dimension of your range space. That leads us into some corollaries related to injective maps, surjective maps, and dimensions. And then we may or may not get to the next few lines of goals, but this gives you an idea as to where we're headed. We'll start actually trying to represent some of these maps in the form of a matrix representation of these maps. We'll talk about invertible maps, which that means they're one-to-one and on-to, or they're injective and surjective. And then we'll talk about isomorphic vector spaces. Isomorphic meaning they're similar. So if you have something that's maybe the space of polynomials of order 3, that's isomorphic to R4, for example. And that's what we're meaning by isomorphic vector spaces. Let's recap by scrolling quickly through what we talked about last time on surjective maps and maybe giving a little bit more information. But a map T, which is linear, it's belonging to this set of linear maps from the input vector space V to the output vector space W. We call that surjective if the range of that linear map indeed equals the entirety of the output vector space W. And that sometimes, instead of saying surjective, you might hear people say that's an onto map. It's onto the entire output vector space. Or another way of thinking of that, if you have a linear map and it's a surjective map, that really implies that every vector in your output vector space W can be reached through this linear map, capital T. Meaning there's a vector in your input vector space, capital V, little v, when mapped through T, will take you anywhere in W. That's a surjective map. One thing that we need to keep in mind is that if we do have a linear map, whether or not that linear map is surjective depends on how we are defining the input vector space and the output vector space. It hinges on that. So here is a question. Let's remind ourselves of one linear map, the derivative map. That's, I'm calling T sub 1 because this is the first example, T sub 1. And let's say that the input vector space is the space of all polynomials of order m, and the output vector space is the same. And I keep forgetting to enclose. I keep leaving off parentheses, but this is now the input vector space v and w are the same. They're polynomials of order m. And we want to know, is this linear map, is this derivative map surjective for a fixed m? So you can now just fix an m, fix it at 2, and think about differentiating a second order polynomial. Does that now get you to anywhere in this second order polynomial vector space? Is this linear map T sub 1 surjective, or is it not surjective? So I'm going to ask this question again with a thumbs up or a thumbs down. If it is, I want your thumb to be pointed up on your chest. If it's not, I want it pointing down, if that's your vote, and I want you to tell me at the count of 3, and I want you to hold it close to your chest so that people can't be swayed by some voting poll or as to what their answer needs to be. So, is up, is not is down. 1, 2, 3. Quite a few thumbs are pointing down, which says is not. Why is it is not? So if we take a vector space of order 2 of polynomials and we differentiate that, then that x squared is never going to be squared again, is it, once you differentiate it once? So you'll just be living with x's and constants. You'll never be able to fill up the second order polynomial vector space with polynomials that contain an x squared term. So it is not surjective. It's never going to get to that particular location or in that direction in that vector space. So that leads into question 2 and another linear map, T sub 2, that takes us from mth order to m-1 order polynomials. And now I'm not going to give you as much time to think about this, but I still want your vote. So if you're playing along at home, you can pretend to vote with your thumb. Up is, down is not, and at the count of 3, is T2 surjective for a fixed m, or is it not surjective for a fixed m? 1, 2, 3. Now we're sort of split, and it may be a little bit unclear since the last one was not surjective, but now if you differentiate but you allow your output vector space to be of order 1 less than your input vector space, you're going to be okay. You can now touch anything in that polynomial vector space that's of order 1 less than what you started. And that's what this is saying. We have a linear map now. So this is T sub 2 is, or thumbs up on this one, T sub 2 is surjective for a fixed m. The way we defined our input vector space and output vector space. It's critical. Do you see it's critical for a map to be surjective or not? We really haven't changed the operation that we're using to perform or to define this linear map, but we are changing the input and output vector spaces. And one gives us a surjective map and the other one does not. The second one does give us a surjective map. The first one does not. So it's critical how you define your input and output vector spaces when you're talking about a map and whether or not it's surjective. Here's a picture of a surjective map, and that's to illustrate, you maybe can't see it from the three maps, since that's not every possible map, but this dot saying that I'm covering the entire output vector space W with the range of T, that's now telling you that this is a surjective map. You can now reach any vector in this output vector space W through the linear map T. That's what this diagram is supposed to be illustrating. Here's an example of a function that doesn't satisfy, or that is neither injective and it's not surjective. Remember what those two really mean. Injective means, or what's the test for injective? Injective would be we have a trivial null space, or we can't get to the same location by using different inputs or from different inputs. And we said, oh, if we just looked at a two-dimensional case, or really a one-dimensional case, if we had a horizontal line and it passed through the function more than once, then it's not one-to-one. If we draw a horizontal line, there's actually two intersecting points, so we can find two different values of x in our input vector space that will give us the same output value. And it's not surjective, so this one's not injective because it's not one-to-one. Our output space W is x squared, and if our output vector spaces was all of R, then it wouldn't be. So here, maybe what I should have said is, how do I want to say this? Suppose that f of x is, let me call this W1, and let's say that W is all of R. So we wanted our output vector space to be all values of R. This particular subset or subspace for this function, W1, it's just the set of non-negative x's. So we can't get to negative values of x, so we are not covering the entire real line from minus infinity to plus infinity in this example. So it's not injective. It actually fails the horizontal line test, because if I looked at f of minus 2, that would give me the same answer as f of 2, which is 4. And my inputs in this case are different, and they're yielding the same output. And it's not in surjective, since the output does not produce negative numbers. F of x, which is x squared, is non-negative for all real values of x in our input vector space. Or we can say then that it's not one-to-one, and it's not onto. And so that x squared, if we want our, so here I'm saying that our linear map, or our map, it's not really linear, but our map is taking an input vector space V being R and our output vector space W being R. Let's look at a linear map example that is neither injective nor surjective. And let's say that our map T is taking us from an input vector space of R3 to an output vector space R5. And what did we call this kind of a map? It's a dimension changing. It's actually growing in dimension. It's going from a smaller dimensional vector space to a larger, and we've actually, I think, used this example before, but now we are going to go through it emphasizing a little bit different points. Let's say that the first coordinate in the output is made up of the three coordinates in the input as minus x plus y minus 3z. And in the second coordinate, let's let that be minus x plus 2y minus 4z, x plus y plus z for the third coordinate, bless you, 2x plus 3y plus z for the fourth, and x plus 2z for the fifth. In this case, if we look at W being the vectors that are in the output vector space and V as vectors in the input vector space, we can see that the span of the following vectors, so now you might try to keep that 5-row or 5-coordinate map in mind, but just look at what I'm doing now to create my first vector, minus 1, 1, 2, and 1. Do you see where that came from? If I put y's to 0 and z's to 0 and x's to 1, that's going to give me one column in my vectors that are spanning my output vector space, and they may not, it's giving me my range of t, which may not be surjective. The second one, let me set y to 1 and x and z to 0. I have 1, 2, 1, 3, and 0. And my third column, let me set z to 1 and x and y to 0 to yield minus 3, minus 4, 1, 1, and 2. And by definition, then, that's really the range of t. This is what we can call a spanning list. And it was created from taking linearly independent vectors in my input vector space, where my linearly independent vectors in the input space were three-dimensional, consisting of the case where x was 1, then y was 1, and z was 1, and all the other coordinates were 0. And this gives us then independent vectors in our input vector space R3. Now, if you are good at seeing linear dependence, you'll actually see that this spanning list can actually be reduced. If I now, let's say I labeled this as W1, W2, and W3, you can show that in fact the range of T is the span of the following two vectors, 1, 0, -3, -7, and -2, and another vector which is 0, 1, 2, 5, and 1. Has anyone had linear algebra before? And did you do Gaussian elimination? Do you remember that? Or row reduction? You could actually take these columns and lay them down as making them rows and do row reduction, and you'll see that only two of these columns are linearly independent. And the one set of columns that will span the range space consistent with these three do not get you anywhere else other than where these two get you. And if you looked at the way I labeled these as W1, W2, W3, you can actually show that this particular column you could think of as minus W2 minus 2 W1, and this one is W1 plus W2. So obviously W3 you can just discard, or it's a linear combination of W1 and W2. Or you could show that in fact two of W1s, and if we subtract then W2 and W3, that will give us 0, the 0 vector. And if they were linearly independent, what would we know has to happen? This now, just showing that that exists, allows us to say that those three columns are in fact linearly dependent. When would they be linearly independent? Under what collection of coefficient weights would we need for W1, W2, and W3 to be equaling 0? So if W1, W2, and W3 were linearly independent, and we said, oh, let's linearly combine those and get the 0 vector, the additive identity, what would those coefficients be? They would have to be 0. They would have to be 0 in order, because one can't be a linear combination of the other, and vice versa. So they're all three linearly independent. The only way that you can add those three, if they were linearly independent, up to get the 0 vector would be if their weighting coefficients were all 0. That's what we mean by linearly independent. And in fact, if this equation is true, then we know immediately that we have some dependency among those columns. We could say that W3 is 2 W1s minus W2. So W3 is a linear combination of W1 and W2. Or vice versa, we could say W2 is a linear combination, or W1 is a linear combination of the other two. Is that clear from that statement? Now, if we look at this, then what can we see? We see that the dimension, or what is the dimension of the range of T? If the range of T is spanned by these two vectors, are those two vectors linearly independent? Can you multiply one by the other? Or can you multiply one to obtain a scaled version of the other? No, because we have at the very top, we have 1 and 0 and 0 and 1 in the 2. There's no way we can make a linear combination of one be equal to the other. So these two columns are linearly independent. They produce the range of t if we linearly combine these in any manner we want. And for that reason, what's the dimension of the range of t? We just have to count how many linearly independent columns we have. The range of t is then 2. And that is obviously less than the dimension of our output vector space W, which is living in R5, or it is 5-dimensional. So we've just shown then that the range of T does not span all of R5, and what does that allow us to claim? T is not onto, or it's not surjective, is it? It's not filling the entire output vector space. Therefore, T is not a surjective map. Also, T is not injective either. And this is what we've already seen before. Recall that we talked about this example before where the null space of this linear map T was actually spanned by this column -2, 1, 1. What does that mean? If I put -2, 1, 1 into this map, what's going to happen at the output? That's going to map that vector into the additive identity in our output space, an all-zero vector. -2, 1, 1. And any linear combination, that's what the span of that means. The span of -2, 1, 1 gets mapped to the null, or gets mapped to the 0 vector. And in this case, the null space of T is that, well, that's a subspace of our input vector space V, which is R3, but in terms of injective, what did we need for a map to be injective? We want a trivial null space, don't we? We want the only vector to be in the null space to be the additive identity in our input vector space. So we would want, for that map to be injective, we would need the only vector to map to the 0 vector in the output to be the 0, 0, 0 vector, and that's not the case. We have a non-trivial null space. In this case, we have the dimension of the null space of T equaling 1, or we actually have a one-dimensional line through the origin in 3D space. And any point on that line will now map to the 0 vector in R5, in W. So we just have to live on that line given by -2, 1, 1. So now if you were trying to visualize this, you could step -2 in the x direction, 1 in the y, and 1 in the z, and draw a line in both directions through the origin, and that line would determine points, or any point on that line, would map to the 0 vector in W. Or T is not injective, or another way of saying that is our null space is non-trivial. And we can look at that a little bit if we wanted, in terms of an illustration of this linear map T being non-injective. Suppose we pick a U1 that's minus 2, 1, 1. What do we know the output is going to be for an input U1? That's in our null space, so this better be the 0 vector, which we know it to be. What if we picked a V1 of 1, 0, 0? That was setting x equal to 1 and y and z equal to 0, and that's the one that we were calling W1 before. That's just minus 1, 1, 2, 1 for an output. So here, T of V1 is minus 1, 1, 2, 1. And if we build up a new input vector, let's say V sub 2, which is just a direct sum of V1 and U1, we now have 1, 0, 0 plus minus 2, 1, 1, or minus 1, 1, 1. And if we apply T of, or apply the linear map T to V sub 2, and if we just did it brute force and we didn't use our additivity property of the linear map, which would be the easy way because we know T of U1 is 0 and T of V1, we know what that is, but let's just plug it in from these values. So set x equal to minus 1, y equal to 1, and z equal to 1. We have 1 plus 1 minus 3, 1 plus 2 minus 4, minus 1 plus 1 plus 1, minus 2 plus 3 plus 1, and minus 1 plus 2. And now simply do the addition. This is why we went through elementary school, so we could do this out. So we could do this math. It's high-level math. There's minus 1. What's the next one? Minus 1. And if you didn't even do the math, you could just copy down T of V1, couldn't you? You know it has to be that because T of U1 was 0. This one is 1. The next one is 2. And the last one is 1. And what this is now telling us is that we now can see that the linear map applied to V1 is minus 1, 1, 2, 1. And that's also the same output vector that we get for a completely different input vector. And if it was injective, we would need V1 to not be V2. If we were getting, we would want for V1 not equal to V2, which is what we have here, they need to go to separate or unique output vectors in our output space, and they do not. So T is not injective. Now, I'm sure you're playing along and you're wondering what kind of combinations we could look at or what we could come up with from this one example, which typically you don't want to generalize from one example, but let's make an observation from that one example. One example is usually good when you're trying to find a counterexample. That's all you need. Typically, one example doesn't make a proof, does it? But it does make a counter example. But here, if we look at the dimension of our input vector space, and that's also the domain, that's the dimension of R3, which is 3. We can find 3 linearly independent vectors in R3. But for this example above, that actually equaled, or if you remember, what was the dimension of our null space? It was 1. And what was the dimension of our range space? We had 2 columns, didn't we? So we actually now see that with that example, the dimension of our input vector space, which is 3, it was R3, is actually equal to the dimension of the null space, which was 1, plus the dimension of our range space, which was 2. Is that a coincidence? I probably wouldn't ask the question if it was. The answer is no. This actually gives us a theorem, Theorem 322, which is labeled the fundamental theorem of linear maps, which says the following. Given V, that's our input vector space, a finite dimensional and vector space. And the reason why I'm emphasizing finite dimensional is when we go into functional analysis, things become infinite dimensional, and some of these results no longer hold. It's nice that we have, or that we are right now working with finite dimensional vector spaces. And I'm assuming that you're all wanting to text this, so you might just say FDVS for finite dimensional vector space instead of typing that all out. Or if you're tweeting, I guess you might just say FDVS in your tweets and everyone will know what you're talking about. So a finite dimensional vector space and a linear map between our input vector space V and W, then the range of T, the range of our linear map, is a finite dimensional vector space, or actually subspace. Then the range of T is a finite dimensional subspace of our output vector space W, and we have the following relationship between those dimensions. We have the dimension of V equaling the dimension of the null space of T plus the dimension of the range of T. And it's interesting to note that this is our input vector space, or the domain, this null space of T is a subspace, where does it live? It's actually a subspace of our input vector space V, and our range space, where does that belong as a subspace? That's a subspace of W. But we can still make this theorem, or state this theorem, that the dimension of our input vector space is equal to the dimension of our null space plus the dimension of our range space. Let's show this to be true, or that it holds, since we now have some tools to use. Let's just assume we know the dimension of our null space. Let's take the dimension of our null space of T, let's just let it equal N, Michigan. Then we have a basis that will span the null space of T. Then there is a basis, and let's just call that U sub 1 through U sub M on that null space. Now, to be non-trivial as far as this statement or proof, let's assume that M is not the same as the dimension of our input vector space. Let's assume M is less than that. And what do we know about basis vectors? U1 through U sub M is a subspace, or a basis for a subspace of our input vector space. We can now extend upon that basis to obtain a basis for the underlying input vector space. We had a theorem on that before. From Theorem, Chapter 2, Theorem 33, we know we can extend or add to this basis on the null space of T to a basis of our input vector space V by adding the necessary vectors, or by adding vectors as necessary. Let's just make that, so we now have U1, U2, up to U sub M. That spans the null space. That's a basis for our null space. And let's now add to that vectors W1, W2, up to W sub N. And let's say that that collection now forms a basis for our input vector space. If that's the basis of our input vector space, what's the dimension of our input vector space? We had M, or a part of it, coming from the null space of T, which is a subspace on V, and then we added in N, so now we have a underlying input vector space of dimension M plus N. And here is a basis for that. So that says if we have a basis, what do we need? We need those vectors to be linearly independent and span the entire space. So these vectors, M plus N of those vectors, span the entire input vector space, and they're linearly independent. And remember what that says, if we put a linear combination of these, what those weights need to be if all of those were now summed to equal 0. The only way that that could happen is if the coefficients on that linear combination of linearly independent vectors could equal 0 is for all of those coefficients to be 0. We'll use that in a minute. But for now, what we need to do to complete the proof because what do we already know? We now know that the left-hand side is m plus n by construction. We know the dimension of our null space of T by assumption, that was m. Now we just need to show or prove that the dimension of the range space of T is little n. Is that clear? We now, to complete the proof, we must show that the dimension of the range of T is n, where the range of T is a subspace of W. All right, so now let's just pick an arbitrary vector v in our input vector space V. What do we know, or how could we or recall that V is an arbitrary vector in our input vector space, and we have a set of vectors that form a basis for capital V. So little v is just a linear combination of those basis vectors. Is that clear? Or we could just label that and say v is a1, v1, or I'm sorry, let me use the u's first. So let me say a1, u1 plus a sub 2, u sub 2 plus up to a sub m, u sub m, plus b1, v1 plus b sub 2, v2 on up to b sub n, v sub n. Oh, I didn't have v's, did I? Have w's. I'm wanting my tablet to complain, aren't I? With all these erasings. That can be done for an arbitrary v in our vector space. It's just some linear combination of our basis vectors. That's all we're saying is little v. Now let's apply the linear map T, because that's what we're dealing with in terms of this fundamental theorem of linear maps. Is let's apply the linear map T to both sides of this equation. And on the left we have TV. Oh boy. And you know what well, never mind. TV, anytime you hear it, you're going to be thinking 501b. What do we have on the right? What is T times any of these U's? So any of these U's, those were vectors that formed a basis of our null space. T operating on any linear combination of those will be 0. Meaning we can forget those and not have to write so much down, and we now have B1T W1 plus B sub 2 T W sub 2 plus B sub n T W sub n. And the reason we could write that is we were using the fact that T applied to any of our U sub L's gives us the additive identity, the 0 vector, for all L in 0, 1 up to little n. because the use of L's are basis vectors in the null space of T. Now, we picked V arbitrarily. Notice that since this vector V that we started with was arbitrary, then we can actually make two different observations. One is that TV, since V was any vector in our input vector space, then TV will span the range of T. So TV will span the range of T and any output vector, TV, that's created from that selection of V can be expressed as a linear combination of TWS's. So TV is just some linear combination, B1, B2, those are the weighting coefficients of TW1, TW2, etc. So TV spans the range of T, and TV is capable of being expressed as a linear combination of the TWs. And that now says, thus, the list of vectors TW1, TW2, up to TW sub n, that now spans the range of T. That's a spanning list. Or we could say then symbolically the range of T is the span of these TWJs. So now we have the TWs spanning our range space. We now need to show that those TWs are linearly independent, and then we can count how many of those we have, which is n, and we'll be done with our proof. Because then we'll have a basis for our range space of T. I keep saying to complete the proof, but hopefully we're getting close. To complete the proof, we need to show that this spanning list is linearly independent so that the dimension of the range of T will be n. Now, to make that statement, or to show that, let's now consider a linear combination of these vectors TWJs such that, so now just assume that we can find C's such that C1 TW1 plus C sub 2 TW sub 2, etc., plus C sub n TW sub n. Suppose we found some scalars that allow that to be true. And that's possible. We can always find a linear combination of vectors to give us 0. Now, from homogeneity, what does that allow us to do with this linear map T? Or how can we now rewrite this equation? If we just looked at it at one term at a time, homogeneity, C1TW1, homogeneity says that that's the same as T operating on C1W1. Which allows us now to make the following. I can now say T operates on C1W1 plus C sub 2 W sub 2, etc., C sub n W sub n, and that is equal to 0. And what do we know now about that vector? That's just a vector that's in an it's the input vector of our linear map T, and it's mapping to 0. So that vector that I've now shown or identified with the curly bracket needs to live in the null space of T if it maps to the 0 vector. Thus, C1W1 plus C sub 2 W2 plus C sub n W sub n as a vector lives in the null space of T. But we have a basis for the null space of T, which means that if that's a vector in the null space, we can write that as a linear combination of our basis vectors in the null space. So, we can expand this vector, which I'm referring to that vector, in terms of the basis vectors, which we were labeling as U sub L's. Since it lies, that vector lies in the null space of our linear map T. Or we can now write that in equation form. We have C1W1 plus C2W2 up to C sub n W sub n. That is now equal to some linear combination, let's say D1U1 plus D sub 2 U sub 2. How many of those did we have? What was the dimension of our null space? That was Michigan, wasn't it? So this is up to D sub m U sub n. Now we have to remind ourselves how we created the W's and the U's to begin with. The U's were a basis for our null space. How did the W's arise? The W's were created to expand or extend our basis so that we now had a total basis or a set of basis vectors for the input vector space V. So the U's were a part of that. They were a basis for the null space of T. We built up, or we expanded on that by these W's, and now W's and U's were a basis of our input vector space. U1, U2, U sub m, W1, W2, W sub n. If they're a basis, what do we know? If it's a basis, then they span the space, which we know, that's all of V, but they have a second property. They're linearly independent. So we know that all these vectors, U1 through UM, W1 through WM, are linearly independent by the way that we built them, or identified them, or by construction. Now, if we have a linear combination of W's and U's, do you see that I could put either of those sets on one side or the other of that equality? And if I did, I would end up with a zero vector on, let's say, the right-hand side. If I subtracted all my DU's, then I would have this linear combination of W's and U's on the left equaling the zero vector. If I have a linear combination of linearly independent vectors equal to zero, what do I know about the weights or the coefficients or the scalars? They have to be zero, don't they, in order to get the zero vector. So the fact that this equality is there guarantees that the C's and the D's are zeros. Thus, the C sub i's and the D sub j's are equal to zero. But if the C sub j's or the C sub i's are equal to zero, then what do we know? Well, we had earlier this equation CTW1 plus C sub 2 TW sub 2 plus C sub n T W sub n equal to zero. And now we know that the only way that that's going to be true is that those C's are zero. What does that say about these columns TW1, TW2, TWN? They're linearly independent. That's what we wanted, wasn't it? This relationship now implies that the TWJs are linearly independent. And now we know that the TW sub j's are linearly independent and they span our range space. And since we know how many of them there are, or I'm getting ahead of myself, then the TWJs are a basis of the range of T, and this list of TWJ vectors, how long is that list? Or what is its length? If we counted each of those vectors, TW1, TW2, we said we had TW sub n. That's of length n. So now the dimension of that range space of T is n. Yes, that's what we wanted. So now we have shown that the dimension of our input vector space V, which is n plus m, is equal to the dimension of the range of T, which was n, plus the dimension of the null space of T, which is n. Couldn't wait to draw that box. The end of the proof. We can actually make some interesting corollaries, or sort of consequences, once we have this relationship, or this fundamental theorem of linear maps. One is corollary 23, which is headed by, which really gives it all away, a map to a smaller dimensional space is not injective. That's the title, or the heading of that corollary. So if we go from a large dimensional input vector space to a smaller dimensional output vector space, we know that linear map cannot be injective. No linear map from a finite dimensional vector space to a smaller finite dimensional vector space. By smaller, I'm meaning in terms of dimension. Can be injective. Or another way of sort of thinking of that is we have fewer vectors. If we just sort of look at the basis of our two input, and our input vector space and our output vector space, fewer vectors in the output space that means that some input vectors must produce the same output. And you know that I just want to draw some clouds to try to illustrate this. Here, let's say, is our input vector space V, and we said we're going to a smaller output space, so the cloud is a little bit smaller. And we're now going between V and W with this linear map T. We are now saying that there may be, or there will be, this collection of vectors that go to the additive identity in our output vector space, which now allows us to create many different input vectors going to the same output vector in W. Here, the dimension of W is small versus the dimension of V is big. And a way to sort of think of the proof is this picture. I've now tried to illustrate that we have a non-empty or a non-trivial null space. We have vectors in our input space, that vectors, not just the zero vector, that will map to the zero vector in our output space V. Another corollary so this one went from big to small and said that can't be injective. Let's look at the other case where we're going from small to big. This is Corollary 24 in Chapter 3, and this is a map to a larger dimensional space. So we're now going from small to big is not surjective. That's sort of the title of this corollary, that it is the title. A map to a larger dimensional space is not surjective. No linear map from a finite dimensional vector space to a bigger finite dimensional vector space, again in terms of dimension, can be surjective. We don't have enough dimensionality or enough information in our input vector space to fill the bigger output vector space. Going to a bigger finite dimensional vector space does not allow us to get onto the entire output vector space. Picture then, there is our tiny v. The dimension of our input vector space is small, and we're now mapping that into our W, our output vector space, and here the dimension of W is big, and sort of what you can think of is now we are only able to get into a subspace of our output vector space. There's fewer vectors. In the input space. And that means that we can't produce all the vectors that we need to cover the entire output space. Produce all vectors in the output space. Or, if this was our linear map T, what we're saying is that the range of T does not span our output vector space, capital W. And that's what I'm trying to illustrate by this smaller cloud or subspace within the larger subspace W. And that's going from small to big, can't be surjective. From big to little, can't be injective. And now what we want to do is start thinking about those big and littles in terms of matrices or rectangles. So now if we start with big and go to little, we're starting with a wide or a lot of columns in our matrix and going to fewer rows. And vice versa, if we go from small to big, now we're going from not very many columns to a lot of rows. And you could start thinking about number of equations and number of unknowns relative to what that might mean for solutions of linear equations. That's one sort of application, and we'll pick up at that point on Monday.